Welcome to today's class on real analysis. Today we discuss some basic definitions of points and topology. So first definition, let X be a metric space and all points and the sets mentioned in the following definitions are subsets of X and elements of X. So first we define neighborhood. A neighborhood of P is a set NRP consisting of all Q such that distance between P and Q is less than R for some R greater than 0. The number R is called the radius of NRP. Let us note that in R1 neighborhoods are segments, whereas in R2 neighborhoods are interiors of circles. So in R1 you have, this is the point P, NR of P is set of all Q such that distance between P and Q is less than R. So suppose that this distance is R, then Q will be somewhere here in the interior or here, not on the boundary. So it is the segment P minus R, P plus R. And in R2, it is the interior of the circles. You consider the point P, then you consider a circle of radius R. So this is your R, and Q will be somewhere in the interior of this circle. So this is the neighborhood in the case of R2. And in R3 it will be interior of the spheres with center P and radius R, etc. Now we define limit point of a set E, where E is a subset of the metric space X. A point P is a limit point of the set E if every neighborhood of P contains a point Q not equal to P such that Q belongs to E. If P belongs to E, where E is a subset of the metric space X, and P is not a limit point of E, then P is called an isolated point of E. Now we define closed set. Let E be a subset of the metric space X. Then E is closed if every limit point of E is a point of E. You know the definition of limit point. If E contains all its limit points, we say that E is closed. Now we define the interior point of a subset of a metric space X. A point P is an interior point of E if there is a neighborhood N of P such that N is contained in E. Now we define open set. The subset E of a metric space is open if every point of E is an interior point of E. So the subset E is closed if every limit point of E is a point of E, that is if E contains all its limit point, and E is open if every point of E is an interior point of E. Now we define the complement of E. The complement of E denoted by E complement is the set of all points P in X such that P does not belong to E. Remember that E is a subset of the metric space X. Now we define a perfect set. A subset E of a metric space X is perfect if E is closed and if every point of E is a limit point of E. So if E is perfect, it will be closed and every point of that set will be a limit point of the set. E is perfect if E is closed and if every point of E is a limit point of E. Now we define a bounded set. A subset E of a metric space is bounded if there is a real number M and a point Q in X such that distance between P and Q is less than M for all P in E. Remember, Q is an element in X and P is an element of E. Now we define a dense subset in X where X is a metric space. E is dense in X if every point of X is a limit point of E or a point of E or both. Now we prove this theorem. Every neighborhood is an open set. Proof. Let X be a metric space and P belongs to X. Let E be a neighborhood of P. That is E equal to NRP for some R greater than 0 in R. So we are considering this. Considering a point P, we are considering the neighborhood of P. So this is the radius. R. So this is our NRP, that is equal to E. Let Q belongs to E. That is, you consider a point here, Q in E. Then you consider this distance that is H. Then you know that the distance between P and Q is, so you consider this distance, this will be R minus H. The distance between P and Q will be R minus H. You know that this point is Q and the total distance is R. Therefore, there exists a positive real number H such that the distance between P and Q is R minus H. So that is this distance. Consider a neighborhood of Q with a radius less than H. So you consider a neighborhood of Q. So you consider a neighborhood of Q whose radius is less than H. So you consider this neighborhood. So its radius is less than H. Consider this. Now you consider a point S in this neighborhood. So you consider an S here. And you know that distance between Q and S is less than H. So you consider all such points. You are going to show that this neighborhood is actually inside this E. It's obvious from the figure, but we prove this. For all points S such that distance between Q and S is less than H. So you are considering points inside this ball of radius H. Now we are going to show that distance between P and S is less than R. It is obvious from this figure that the distance is less than R. Distance between P and S is less than R, so that S is in the interior of E. We have distance between P and S is less than or equal to distance between P and Q plus distance between Q and S. And you know that distance between P and Q is R minus H and distance between Q and S is less than H. So this is less than R minus H plus H. So this is equal to R. That is, distance between P and S is less than R. So this implies S belongs to E. It is actually NRP, neighborhood of P. Therefore, NHQ is actually this one, this neighborhood NHQ is a neighborhood of Q contained in E. Therefore, Q is an interior point. So we have chosen Q arbitrarily. Q is a point inside E, and you have seen that it is an interior point. Therefore, every point of E equal to NR of P, neighborhood of P, is an interior point. Therefore, E is open. So we have E is a neighborhood of P. Therefore, every neighborhood is an open set. Therefore, every neighborhood is an open set. So this proves the theorem. That's all for today. Have a nice day.